Hello, I'm Bradley Sward, Associate Professor of Computer Information Systems at the College of DuPage in Glen Ellen, Illinois. And this video is going to take a look at, this is our first video that takes a look at x86 assembly language and basic fundamentals, just the basic syntax of just getting something on the screen into our program and something that might actually compile, nothing that's going to actually functionally work, but just the basics of just, getting the foundation of the language put together. So when it comes to things, there's what can we deal with? There's syntax, right? There's operations, there's operands, there are data segments, code segments, registers, and variables, and all sorts of things. So let's just get used to it. Again, a lot of this you've already, if you've done any other language, you know a lot of this stuff. It's just that it seems like some of this is completely reversed when it comes to the way it works in assembly language, and it's just because it's so low level compared to even C, and then as you work your way up to Java and Python and beyond with all this kind of stuff. So an integer constant, so let me move my body over here. So an integer constant is exactly what you think it is. It's a literal value, like the hard-coded, there's a different, different terminology, hard-coded, integer constant, literal value, just a hard-coded 5 or a hard-coded 19 or something like that. So constant expressions, literal immediate values. The book uses quite a few terms for it, and I try to keep to one or two different terms, but it's hard sometimes, especially when you're teaching multiple classes and the terminology for the same thing is different somehow. I don't know why we can't all just agree on one terminology. But an integer, a hard-coded number, you can put a positive sign in front of it, or you can put a negative sign in front of it, right? So if you have a 7, you can just put 7, and if you have a negative 7, you have to put that negative in front. But if you want for positive 7, you could put a positive value in there, put the little plus sign in front. And so assembly language, when we're dealing with this, most languages allow us to use different formats when it comes to the numbers that we put into the programs, so the compiler or the assembler breaks them down. So we have access to 4 of them. Octal is something we've never touched, at least in this course, and I haven't seen octal used in a long time, so I don't know exactly what octal is used for in modern day, but we definitely use binary, we definitely use decimal, and we definitely use hexadecimal. I know everyone is sick to death of all those videos and trying to convert from binary to decimal and so forth and so on, but now we finally get to put all that hard work into practice. That's why we're doing all this, is so that we can, so when we go and print out registers and we see everything in hex, that we know what we're looking at. We see a 19, we don't go, what is that? That's actually 25, things like that. Our brain we can start thinking like a true programmer as opposed to someone else. Okay, so coming back, integer constants. So if I put, coming back, so there's a little b, a little o, a little d, and a little h. And if you forget, it just presumes to be a decimal format. So if I can put 30d down for a value, for an integer value, and that's represented in decimal format. Or I could just put 30, or in this case, like 42. Just by itself, a number is represented in decimal format. So if I want hex, I got to finalize everything with a lowercase or just an h. 6AH, that's hexadecimal format. 1101 binary. So when you do these kind of data formats, the assembler is pretty good at telling you if you screwed up, like if I use a letter that isn't part of the hex format, it's usually pretty good. So one little rule, though, that you have to understand for these kind of integer constants is that if I start with a letter, especially like a negative value or something like that, I have to start the number with a 0. And that's just because of the way the tokenizer and just everything works when the assembler is breaking down your actual programming code into tokens so that it can generate the machine language from it. When it sees a letter to start a token, it goes down the path of trying to figure out if it's a function call or a variable name or something like that. But if it sees a 0, it knows it goes down a different path and works its way toward figuring out that it is an actual number that we're looking at. So it gets deduced a different way. So it's one of those tricky ones. If you forget this little detail, occasionally it'll pop up. You'll get an error in your program. And you'll be like, what the heck is wrong? Just remember, anything in hex has to start with a number no matter what. So that's pretty much all there is to do. You've done these things. I'm saying C++ allows you these different data formats. The syntax is different, but you can represent a number in binary and hex and so forth and so on. Okay, so integer expressions, so it's like, so there's a big difference here between an integer, just a hard-coded, a single number, versus something that is a combination of integer constants. And so you notice here there's no variables involved in any of this stuff. This is all just hard-coded numbers, 16 divided by 5, negative 3 plus 4, you name it. There's no x, there's no y, there's no a, there's no total, there's no sum, there's no nothing. And so an integer expression, because they're all hard-coded numbers, can reduce down to one single result. And as you see here, 16 divided by 5, integer division gets me 3, and so forth and so on. I won't bore you because you can see for yourself all of that kind of stuff. So, oops. And so I'm just trying to move myself over a little bit more here. Okay. And so the regular PEMDAS rules apply. There's no exponentials in assembly language. Most languages don't have an exponential these days, or at least C++ and whatnot. But you can see parentheses come before unary, but come before multiply, divide, come before modulus. Modulus is basically just a division. We learned that in chapter 7, quite a few videos in the future. But a modulus is just a division where you take the remainder instead of the quotient. And then plus minus, addition and subtraction comes on the back end of this thing. So there's a huge difference here. If I want there's between the values, parentheses, I guess I'm not showing it, if you want to change the order of operations, that's when you have to use the parentheses. Because if I didn't have the parentheses for this one, the 35 one, it would read negative 3 plus 4 times 6 minus 1. It would read, and the result would be completely different at the end of the day here. And so so you'll see for a lot of these kind of cases, if you do use a register or a variable when you get to that kind of stuff, if it can't reduce down to a single value, it's generally too complicated. This is not a high-level language. Assembly language is as simple as it gets. It's a one-to-one relationship. So if the line of code you write in assembly language cannot be reduced to one line of machine code, you're going to get an error. And so it's very common in all high-level languages that one line of code in that language reduces down to many, many, many lines of code, multiple lines of code in assembly language, and then thus machine language. So just keep that in mind. Let me show you an example of this through the disassembler in Visual Studio. Okay, so don't freak out too much about what you see in front of you. Just take the main bullet point here. And so I have a little tiny program. I set x equal to 4, and you can see, don't mind dword pointer, x, whatever, comma 4. You're gonna see this later in later chapters. So don't freak out now. You have plenty of time to get yourself acquainted with this. But you see, I'm setting it to 4. I mean, because it is 4, right? So I'm putting 4 and moving it into x. And that is the way I would do that in assembly language. But notice here, using an integer expression, 3 plus 6 mod, this, that, whatever that end result is, the assembler, before it puts it into code, like the actual machine language code, reduces that number down for us. Because there's no reason to do all of this work at runtime, correct? Right? Because it has a hard-coded number, so it reduces down automatically for us. So in this case, I don't know, I just put random numbers in with random operators, but I get a 2 out of that. And so the 2 goes directly in. So if I did go ahead and set up another, let's just say int r equals 3 or something, and then just go ahead and say, okay, now I'm going to divide by 4 divided by r plus. I'm just adding random stuff again, and I run this program a second time. You can see, when I hit my disassembler, bring it over here, you can see that now things have greatly changed because it's no longer a constant value. So, so setting r to 3, the same as before, blah, 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 but x to 4. But now this whole equation is much more complicated. CDQs and IDIVs and all this, and move statements and adds and all sorts of crazy stuff. As a moment ago, because it was a hard-coded integer value, it was a lot easier to do, but now it has to do so much more work to get us to the end result. And so the compiler, the assembler, is not necessarily smart enough to be able to reduce this down to absolutely as minimal as possible. A lot of times the assembler, especially with optimizations off, will not do a great job of doing more than just brute forcing what it sees in front of it. And so you have to understand that. Like, you have to start thinking. This is part of the reason why we take this kind of course, is if you can start thinking smaller and start thinking into smaller lines of code, and just kind of breaking your thoughts and logically turn them into smaller code, you're going to have faster, better, and more maintainable and easier to read code. You honestly are. more lines of code isn't a bad thing for me anyway, because a lot of times simple statements that kind of, 5 or 6 simple statements versus 1 or 2 ginormous statements when it comes to what's going on in a line of code, especially without comments, you generally can see the flow a lot simpler. Well, assembly language is its own thing, but I just want to say that it's its own thing when it comes to having uncommented code. But just to show you here, the proof is in the pudding here when it comes to that sort of stuff here. So let me bring this back to, here we go. And so that's all I wanted to say about integer expressions versus variable expressions. Okay, so characters and strings. So when we're dealing with strings, this is, if you know Python, you kind of know how this is going here. You can use single quotes or double quotes as long as you're consistent, and you can embed single or double quotes inside of the other. Just like this, say good night, Gracie, that you can put a double quote inside of a single quote. Python allows you the same stuff. C++, Java is a lot more strict when it comes to that. You have to use single quotes for specific individual characters, but you use double quotes for strings, basically an array of strings. And everything we're going to do here in assembly language uses 7-bit ASCII. So it's 1 byte per character, 1 byte of storage per character for any character inside of a string. So you'll see when we do this that we're going to set up a byte array. Okay, so we know reserved words, right? Like you can't name a variable if in C++ or Java, and so forth, and if and for and while and class and dynamic cast and all these weird, everything. We know most of them when it comes to keywords and things like that you can use when it comes to the higher level languages that we program with. But some of them in assembly language are quite bizarre, and sometimes you'll see like the C. Just plain old C is a keyword, because C is a language that assembly language works with, so C is a keyword. And DD is actually a keyword, and things like that. And you're like, why did I set up a variable called DD and it doesn't work right? And I get a compiler error, something's wrong. And same with C. I used a variable called C, and I can't run my program. And so you kind of have to get used to that. There's an appendix in the textbook that shows you the comprehensive list. So you just kind of look at that and just commit some of them, the ones that look like they might be common, like C and DD, those are things that we might use. Commit that to memory. And so reserved words are mnemonics, right? Directives, operators, operations, predefined symbols, things, like an if, the word if, or the word move, or add, or like in this case, C and DD and things like that. And so it just gets, we say the names are going to be pretty similar to what you expect them to be. We're going to see that very soon here, that the actual operations and all those kind of things are going to be they're going to sound like what they actually do. That's what the word mnemonic is all about. So identifiers, otherwise known as variables, otherwise there's so many different terms for these stupid things. A variable, an identifier. So it's keep to the same rules for every other language, and then we don't have to worry about anything. So underscore or a character, a letter character to start uppercase or lowercase. You can put numbers in there as long as it's not the first number. Don't test this limit. Don't be that one that tests this. I'm told that you have to have your identifiers under 247 characters in length. And why would you ever want to do something like that? Java is famous for having large names for things, but that is quite large. That's basically a whole paragraph right there. So, how many 50 words you could put in there? 4 or 5 byte average per word. So yes, but keep your, we're going to see here, make your names count. Don't just use A, B, C, and D. Use total, sum, and whatever else that you're trying to do for variable names. And also, this is something that you have to get used to. It's different. There's no case sensitivity in assembly language. So you could write any kind of crazy font. Please don't. Stay consistent. But the lowercase x and uppercase x are the same variable inside of assembly language. They would be completely different variables inside of C++ and Java. Okay, so directives. This is one of those. This right here, boldface, underlined. Let me move my body out of the way so you can see this and you go, oh my God, look at this. If you do not see a directive in any of the PowerPoint slides or any of the videos I use, you're never allowed to do it for a homework assignment or an exam. And I can, now that I have video proof of this, this is absolutely 100% forbidden to use some of these crazy MASM directives that we use, that I see used out on the internet and everywhere else. And the reason for this is, what are directives? They're not part of the Intel instruction set. So that means they're not actual assembly language. They're just part of, like pound include for C++. It's a preprocessor directive. These are just, it's called a directive in C++. And it's the same deal here. I'm not teaching you C++ if I just put a .if. I'm not teaching you C++, I'm not teaching you assembly language if I do .if or something. I'm not teaching you assembly language if I'm using the uses statement or local or just local or all these other directives. And so it's my job to teach you assembly language, and assembly language you shall learn. So that's just why it is the way it is. So the textbook might be at odds slightly with what you learn here, but ultimately at the end of the day, the way I do things, as much as it might be a little more code, it's simpler than the way things end up. Trust me on this. If you follow a pattern and you follow an algorithm and you find a way to take a problem and break it down into its parts and just basically translate line for line, at the end of the day, you're going to do great. And so, and also then, if I did use these directives, if you went out into the real world and you had to use assembly language, x86 assembly language, you wouldn't know what to do, because they wouldn't. Maybe use NASM or a different assembler or something that's even simpler, and you don't have access to the same stuff, and you're like, I don't know what I'm doing anymore. This is exactly why I'm teaching you the actual commands in x86 assembly language. Okay, so the operations themselves, for the next however many weeks, it's going to feel like there's plenty, like 5 to 10 new operations per lecture. And it is true. And what is an operation but like an add? Add two numbers together, subtract two numbers, move data from one place to another, and so forth and so on. All the things you know how to do in high-level languages. But again, remember, we can only do one tiny little thing at a time. The CPU can't handle these massive operations, and what it does is it has to break it down into smaller and smaller pieces. So for any operation, there's a mnemonic: add, sub, neg for negate, inc and dec for increment and dec, and so forth and so on. And for every one of those, there's going to be a number of operands that you need. And we'll see us in a slide in the future here. It'd be like some need 1, some need 2, some need 0. And some need 3, and actually some need 4. Some of them get pretty crazy. And so, like with this, move ECX comma EAX, which just basically, the move is just an equal operator, which just means ECX equals EAX. All right, that's fair enough. And here's a label called again. And so notice here there's a semicolon, which is completely different than what you're used to seeing in C++ and Java and C# and all that. The semicolon is a comment in x86 assembly language. So it's a line comment, just like // So this is a comment optional-ish. We'll talk about this, and you'll see this in plenty in the future. Like if something doesn't work and you just throw it in for me to grade, and there's no comments, I'm not going through this. I have to grade hundreds of these things over the course of a month or even a couple of weeks sometimes. I'm not going to spend the time to figure out exactly what went wrong with your problem when there's 100 others that might have the same kind of things, and I can't take hours upon hours to fix your problems. So if you leave a comment, you can help yourself, because come back tomorrow, right? You write your code, the next day you come back, or you come back a week later to finish up the problem. You go on a vacation at work, you come back, there's no comments on your code. How do you remember what to do? And I didn't write the code, so why would you expect me to understand how your code works when it's written at the lowest level imaginable? So a label, if you've ever used a go-to statement in C++, shame on you. I'm not going to name any students by name, but there's one that moved out to St. Louis area just recently. Shame on you, Mr. Man there. So doing that in a super advanced C++ course. But a label is the only way we can jump around in assembly language. Basically, it is a go-to. Like for something like this, again, you're not expected to understand necessarily what's going on. This label, when I hit this loop, a loop statement basically is, should I continue looping? Yes or no? And if the answer is yes, I have to tell I have to know where to go back to, so I have to set up a label. So basically a pointer, and be like, you go back to this memory address so you can continue and you can loop again the code that you see. And so loop, 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 and then eventually you would fall through when the loop, turns out to be a false statement. And the labels follow the same identifier rules, but code labels end up just being targets of jump instructions, which just means they end up being memory addresses. Whatever memory address this line of code is actually stored in the code segment is where we would come back and loop to if we needed to do so. And so that's pretty much labels. Oh yeah, a lot of times you'll see that, when it comes to labels, you have to make sure that you name them all uniquely, just like variable names. See, sometimes you're kind of at odds, especially if you have a lot of these things, a lot of labels kind of tightly knit together, a lot of if statements, a lot of elses and for loops and all sorts of things. You have to make sure you have your labels set up so you don't accidentally have a name clash, so the name is in 2 or 3 places at once. And I know you have to deal with that in any language, but there's a lot more going on here, and especially with all the little wires moving around, little jumps and all that stuff, it does get confusing sometimes. So just beware of that kind of stuff. Okay, so here are the operations themselves: move, add, sub, mul, div, xor, nag, inc, dec, jump, comp, compare, that sort of thing. And so they're memory aids. If they were just named A, B, C, D, E, F, G, that would be really difficult to memorize, right? So it's very helpful that they pretty much sound out and do exactly what you might think they do. Not everyone is exactly like that. There are a few that go off the boards and they feel like they're crazy, but at the end of the day, the ones that we use most of the time is perfectly fine. And again, for every operation, we have to get used to understanding how many operands, basically how many parameters, how many little things do I have to attach to an operation so the operation can do its job properly. And so the types of things that we can put into as operands to these operations are as you see here. Constant, immediate, hard-coded literal values like 5 and 17 and 19, 22. Constant integer expressions that still get reduced down. This is like 1a and 1b if you want to think of this, because this at the end of the day still gets reduced to 13, which is a constant immediate value. So 1 and 2 kind of work hand in hand. And remember, I just showed you a few minutes ago in that video showing you the disassembly that once there's a variable involved, it complicates things up so much that assembly language would not allow that to happen. And so other things, we've discussed registers briefly, right? We're a little bit further on here, so at least you understand what a register is. It's just a variable, a strangely named variable that sits on the CPU. That's all a register is, and there's only a few of them. You don't get to rename them or anything like that. And the other type 3 of the operands that you can have is basically memory, a variable, something sitting in RAM, basically a memory address in RAM that holds some kind of value. And in this case, I named it, it's called name. It could be called X or Y or total or sum, you name it. The computer can reduce it down. And so again, for every instruction, you can have a variable number. It depends on the instruction, how many operands it needs to do its job. Set carry flag doesn't need anything because you already have all the information we need. Let's take the carry flag and set it to 1. What more information would it need to do its job? The answer is 0, nothing. So like for these guys, inc and dec, I'm trying to increment, add 1 to a value. And so all I have to do is, what value do I want to add 1 to? Well, how about we add 1 to whatever's in the EAX register? How about we add 1 to whatever is in the score variable? And so that's all we need to do, because we're adding 1 specifically. But for these guys, these need 2. We need to say, oh, I want to add EBX and ECX. And we haven't discussed any of the individual operations yet, but just understand that the add is like a plus equals, and the sub is like a minus equals. And so it basically says EBX equals EBX plus ECX, and score equals score minus 25, and so forth and so on. So just kind of whetting your appetite now, so when you get to it, it's not as scary. And then other ones like extended shift right something or other. We don't never use this thing, and I just fly right through it in a future video. And so do this for, and it needs AX, DX, and 4. It needs 3 specific operands to do its job. It need, so how does it work? Yeah, whatever. Look it up. And I don't know if anything needs 4 offhand, but I say this is about as, I mean, anything more than 2 is rare when it comes to an assembly language line of code here. Okay, so comments. So coming back to this again. So you should start commenting to your code. Watch my videos. Watch. I hope I put comments. I don't remember now because I'm coming on the tail end of this. Like, you better start commenting your code, especially in assembly language. And so when the purpose, of course, is to understand what the heck you're doing. And what I like to do, my way of commenting code is basically on the first line of a block of lines of code in assembly language, I go ahead and I put the comment for what am I trying to do, as if it were like C++ or even pseudocode. Just something that explains I'm trying to set A equals B. And so I'm not saying literally that, or I guess I am, every line of code. And so even with this, you'll notice that we need 2 lines of code to set a variable equal to another variable. So it's not even commonsensical, when you're just trying to set something equal to another thing. It takes 2 lines of code. So I put the comment on that line of code and say, this is what I'm trying to do. And then basically I don't comment anything else until I'm finished with that line of code in C++, and I'm ready to try to translate the next line of code. And so basically, sometimes that one line of code in C++ is 1, but sometimes it's 3 or 4 or 5 or even 10 different lines of assembly language. And so at the end of the day, if something goes wrong, you can kind of work your way back to seeing which line of code, or at least in C++, which line of code is breaking on me, so that I can kind of delve in and go, how do I fix this in assembly language? You really have to take your time on this. You can't just hack this out, build the whole thing together, and then try to cobble it all when it's all said and done. You have to build this in logical order. Okay, so future you, anyone else looking at this code, the person you want to grade your work and give you a nice grade will be very happy if they can read and understand what the heck your code is trying to do. So let's see, do I show comments? So we showed it earlier, and so what you do is you put the comments, this is a little different than other languages, you put the comments off to the right. You see how this is all set up here? And so everything, you make sure everything starts on the same column, because you're going to notice there's basically your brain is going to overload staring at all these symbols and staring at all these lines of code. And if you just throw the comments in and just willy-nilly throw them and pepper them in with everything else, it's just a lost cause. So you put the comments off to the right, starting at the same column like you see here. And notice even for this write out value, it's 2 lines of code before I move on to the loop. And so because I need to put a value into the EAX register before I call this function to write the value out to the screen. Again, future video, but just understand that. This is how I expect to see you guys with your comments, and so at least to start with. Semicolon, I'm not even going to show you how to do the multi-line comment. I never use it. Even in other languages, I just use // or I use the pound operator or whatever, hashtag or whatever you want to call it, octothorpe for Java. So just use the semicolon, and it's hard for a lot of people who've been programming in C and Java to get used to that, because I'll see semicolons in a lot of places at the end of assembly code, and I'm like, you don't need that. It's not, this is not, it's assembly language here. This is not C++. Okay, so code standards. I've seen, I'd like to say I've seen them all at this point, but every so often someone surprises me with how different their code looks than everything I've ever seen in at least the 5 years I've been doing this course now here at the college. So as long as you're consistent, I'll try to push you. You could watch my videos. I really would love for you guys, because that's the standard way, or a pretty standard way of doing things, is the way I write my code in the videos. And so, but at the end of the day, as long as you're consistent and you don't go absolutely crazy, you can kind of do whatever you want. This is a little different than every other language I teach, where I try to force you to treat, an Allman code formatting standard, or just to try to work you to always have curly braces and just all these little rules. Assembly language, I understand it's a very difficult course. We've all been there. This is like organic chemistry of computer science. If you understand, or you understand where I'm coming from, if you know that reference too. So just do what you need to do to get the job done. Capitalize nothing, capitalize everything, just the reserved words. This is usually how I fall down. I usually capitalize just the reserved words and not the mnemonics, but like offset and whatever and those kind of things, and data segment and stuff like that, that gets capitalized, but nothing else generally does. And so in general, then this applies across the board for any language and any code you'll ever write. Use descriptive names for your variables and your functions. So like without boring people with my stories, I made a game when I came back into computers, what, I got 14 years ago now, and I have this function. It's uncommented. It has 16 variables passed in it, and they're named A1, A2, A3, all the way up to A16. Everything in my entire game uses this thing, and I went back and looked at this recently, and like, no clue what it does. No clue, but somehow it does everything. And if I get rid of it, the whole game goes to crap. And I'm like, that is not good engineering, but that was me 15 years ago as a programmer. And I learned my lesson well, that that's not going to get me places, especially if you got to work with other people and you got to get a job done and you got to maintain your software for years at a time. Space everything out. You're not going to win any awards with me for condensing your code into the tiniest little tightest ball imaginable. Space things out, make things easier to read. If once you've seen thousands of lines of code a day in your day-to-day lives, you understand sometimes your brain, at least with my brain, it needs to be spread out a little bit. Your brain might be different, but that's just the way I've learned the code that I've seen over the years and all the jobs that I've had. Indent. So it's like indenting code. Coming back here, notice how, where is it again? Here we go. The code itself is indented one time over, and labels and things like that are not. So you're not just gonna, because the one thing I know, how do I know you copy pasted from the internet? Everything is just slammed with no formatting whatsoever. You have perfectly working code, hundreds of lines of perfectly working assembly code, but there's no way you could read that because it's just copy pasted from the internet. So just, and weird thing here, like if you do a doubly nested loop and those kind of things, you don't doubly nest like you do in C++ or Java. You don't doubly nest the loop code. You basically, all the code runs on the same column, whether it's looped once or it's in one loop or 6 loops. It's kind of weird. It's definitely different, but that's just the way things go. Let's see, start operands for all. Yeah, and start everything on the same line of code. You'll see as I'm coding too that I save enough space for the operands or the operations themselves for 5 letters. And so I'll start in basically MOV or something, and then I'll put a space or 2 in there so that all the operands themselves start at the same column. And it's not just being OCD again, it's just one of those things. If all your code is just kind of flown about and just kind of flows wherever, you're not going to be able to understand what's happening. You might today, but you are not going to tomorrow. No one else is going to read that way, and when I go to grade things, I'm not going to be able to understand why your code flows out and comes back and does all sorts of crazy things. So we've already discussed commenting on the right side, on the right column, all lined vertically together and spaced out. So here is an example, and this, I do not want to see anybody doing this. This is not how you do things in our course, but just to show you an example, .386, these are all things that have been deprecated. We don't need them in the Irvine library, but you get the point here. Notice how everything's left justified. The code gets tabbed over once. Everything we're never going to use invoke. We're going to use call and stuff like that. That's how I know you didn't. How did you never watch my videos if you're using all these things that I never taught you? Just how did he know? It's pretty obvious. So, but anyway, notice that most things line up at the same columns. The comments are on the right, starting at the same column, and so forth and so on. And again, this is a 16-bit program, so this does not apply to anything we'll ever do. So this is your template. This is your hello world minus hello world template. Your global variables will go in the data segment. Your code itself will go in the code segment. We never have to worry about the stack segment directly. We can set a title. Why doesn't anybody ever put their name and the purpose of the program in there? Why is it always left name, purpose here? Who are you? Whose code am I grading? Like, why wouldn't you put your name in there at the very least? You'll always need to include the Irvine library, which there's other videos to show you how to use all the functionality of the Irvine library, and then the rest is up to you. So this is your, if you put this in, you get, if you follow the instructions and get Visual Studio lined up with the MASM, with MASM install, perfectly fine. You run this code, basically you'll get the window that pops up. It'll do absolutely nothing. At least you know it's working. That's like 95% of the battle. It's just at least getting everything going in Visual Studio, is getting that first program just to do nothing. And then at least you know you can go from there. This slide shows you what is going on when you take your ASM file and you try to turn it into an executable. And so your ASM file goes through the assembler. It is not a compiler. A compiler takes high-level language and converts it into assembly or object code. But the assembler turns assembly language into object code. And so it also produces this optional listing file. I think we described that in a future slide. Yep, I do. Next slide. And then so that's basically just to help you see what your program is breaking down into, because you're taking something large and breaking it into smaller and smaller parts. So every individual ASM file gets broken down into its individual OBJ file. And that actually applies to C++ as well, and probably every other language, many other languages, they break down as well. You go into C++, you go into those folders, you can find the OBJ files, because it's just broken down assembly language. It's basically just machine code prior to the next step, which links everything together. So we're going to take our code and link it together with the Irvine library. We're never going to have, in this class anyway, we're never going to have more than one file going at a time. It's hard enough as it is, so just one file, and it links with the Irvine library functionality to produce the final executable file that we can run. And that's just how things work. And then of course, this isn't when I actually want to run the program. We have to get permission from the operating system, because this thing is just a series of ones and zeros sitting on an SSD or an HDD or whatever hard drive. And so what's happening is you ask the operating system to run this program. It loads it. It uses an OS loader utility, which takes the program from the hard drive and copies into RAM, and then wherever the operating system sees fit, and then goes ahead and starts running the program, and then you can interact with it, whatever the program is supposed to do. So listing files, map files, they all have the same basic theme, and they're just taking the copy of the source code, and they show you more, again, a lower level understanding, memory addresses, byte for byte, hexadecimal, machine language representation of what the code is actually going to look like, and then you can actually see variables, constants, everything else. So I mean, this is for compiler designers, that's nerdy dream stuff, right? Be like, how did I take assembly language and actually convert it into all the tons of machine language ones and zeros? And that's a huge task, right? I mean, could you imagine, like, whoever writes these compilers, whoever develops these compilers for all of these languages? I think it's an amazing tool. As long as you follow the rules of the language, the syntax of the language, and you make a program that follows the rules, the tool will make it work. I think that's just amazing. I mean, just having gone through a couple of those classes in my undergrad days, I know how much work that truly is. Okay, so now here are the start of your best friends here. This is how do we get going here. Let me break this down here, and let's start talking about this, and I'll have Visual Studio open as we do this. So basically, these are all the data types that we're going to need for this entire course. This is and some of these we're not even going to use. We're only going to use 1, 2, and 3 here for the most part. We never actually use quad word, and we never use tbyte for 10 byte. 10 times 8, 80 bits of storage. I don't know what that ever gets used for. But byte versus signed byte, word versus signed word, double word versus signed double word, and so forth and so on. What you see here is that the default is the complete opposite of every other high-level language. By default, if you just put word or double word, it's unsigned. If you put int in Java or C++, you get signed, and Java doesn't have unsigned, so let's just talk C. But I have to put an S in front of it to indicate that I'm dealing with a signed variable. And just like in C, I would have to put unsigned. So complete opposite of what we're expecting to see. But what we're understanding, a byte is a byte, 8 bits of storage. A word is 2 bytes, 16 bits of storage. And a double word is 32 bits of storage, 4 total bytes of storage. And so just for the first test, you have to understand and just memorize these kind of, what's a quad word, what's a signed quad word, what's a t-byte. But at the end of the day, we don't have to go any further than just understanding this, and just because these three, 1, 2, and 3 is where we're going to spend 100% of our time. And so there are floating point. We never actually get to the floating point types. Real 4, real 8, real 10. And as you can imagine, real 4 is the 32-bit IEEE 754 standard, otherwise known as float. And real 8, 64-bit standard, otherwise known as double. And real 10 is long double. So say this does not change. This is, between processors, everyone has pretty much agreed that these are the standards for float, double, and long double across the board. Int and all these other things, they might have slight differences, but this is the standard when it comes to floating point data. Real 4, real 8, real 10. And defining variables. So you're going to set up a variable always, at least a global variable. This is pretty much everything except for the last couple weeks of the course. A variable is put into the data segment. A variable is a global variable. Again, complete opposite. We're so used to using local variables for everything we do in C++ and Java and so forth and so on, but we do not do that, at least up front here in this course. So everything has to go in the data segment. And as you can imagine, everything, basically we're trying to produce the smallest, most compact program imaginable. So the data segment will take everything you put in here and condense it down into the smallest amount of space possible. Higher level languages do not do exactly that. There's a lot of bloat in a lot of higher level languages. So as you can see here, int x equals 10, like, what am I trying to do? You have to go back to over here and just try to figure out what am I trying to convert into. And so there's a slide in a previous video that shows you our 32-bit environment, and it shows you that int is a 32-bit, int is a double word, it's 4 bytes. Short is 16 bits, which is a word, and character, char, is byte. So we just have to understand that is what we're dealing with. Those are the conversions, and then the signed and byte and signed and unsigned versions of that. So an int would be a signed double word, x is the variable name, and 10 is its initial value. And so like sum double word 0. And so that's how I set up a variable, and I can prove it by trying to build, and you'll see that everything was happy, because if I screw it up and just put something like one sum, that name is not allowed, you will get an error, and you'll say error, syntax error sum. And you will notice very quickly that the error messages in assembly language suck. I can be honest with it, because they don't tell you very much. They're just like error. It's like when my mom calls up and goes, "The computer doesn't work." Like, what's wrong with it? I don't know, it just doesn't work. That's not very helpful. And so a lot of these errors, because this is a very old system, the MASM assembler, very low level, it does not give you as much information as compilers do in the modern day. So here's some double word, I could put total signed byte 2. So this is basically a character, a signed character, just a normal char. This is an unsigned double word, right? So and then of course there's just something else just called x, and I'll just say word, and then I can actually, this is a future slide, just put a question mark, and that indicates an uninitialized variable. So this is a word, which is an unsigned 16-bit piece of storage. It's called x to me, and it starts out the program uninitialized. Okay, so again, defining the variables, we have to know our ranges. We have previous videos on that. Byte can only go from 0 to 255, right? Word can only go from 0 to 65,535. Sum can only go from 0 to 4.29 something billion. You get the point here. MASM, MASM doesn't give errors or warnings. Does it though? Let's see. If I put 267 in here, will it give me an error? And yes, initializer magnitude too large for specified size. That's great. At least up here, at least I'll get at least that error message tells me what's going on, because I can't fit that number into a signed byte, and I can if it was 25. So we have to know our ranges. And not only do we have to know our ranges for this, we have to know our ranges so that if our program is running somewhere out in the real world, that we make sure we don't overflow or underflow and cause huge problems, like in that previous video with the slot machine issue, that the woman thought that she won $4.3 million when she only won maybe 20 bucks, because there was a slight calculation error, and I'd be fighting for my money too, even if I knew what was going on. I'd be like, give me my money, give me my $4 million. So just understand that. So let's see, and who cares about the debugger? There'll be plenty of time to discuss the debugger here. So here are, basically setups. I'm not going to go through everything here. So for all the byte values, you can use ASCII values for bytes. So this would be what, 60, 65, or 97. I can't remember. I can never remember lowercase versus uppercase. I just can't for the life of me. But this is the smallest unsigned, 0. This is the largest unsigned, 255. As signed quantities, you go from -128 to +127. Here it is uninitialized, and as I was showing you before here, you try it, 256 is a byte, and it tells you that it's not going to work for you, but 255 is perfectly legit because that's a value in the correct range. And again, notice that when I'm setting up my variables, there's nothing at all in the code segment. Everything is set up only in the data segment here. And so you'll use these inside of the code over here, but you define them in the data segment. And so same basic stuff, you just understand the ranges get larger and larger, and you can see the values over here. So I'll just kind of go through quickly. This is kind of a weird one, that you can set up a word, which is 16 bits of storage, with 2 separate ASCII values, because every character is 8 bits of storage, so I can set up a double character inside of here. And you can actually do that in C++ as well. It's crazy. I didn't believe it. I could go into C++, set a character, and put quotes instead of single quotes, double quotes, and put 2 characters in there, and it works, and it compiles. I just thought it's like, okay, like who would ever design that? But you can do it. And so just again, remember about making sure the values that you initialize are legitimate, and you can actually make them work so you don't get that error. And so 32-bit, from 0 to 4.2949 billion, and negative 2.14 to positive 2.14 billion on the signed end of things. Uninitialized, out of range, same deal. Just again, larger numbers can be stored in larger spaces. That's like a duh kind of thing. And so here, fill in the rest of these. Again, you just have to understand that they exist, and just kind of remember what they do, but you're never going to use them in this course. There's my real 4, my real 8, my real 10, my t-byte, my signed quad word, my quad word. For whatever reason, there's no such thing as a signed 10-byte. Try it yourself if you want to. It's no big deal. But just these are the remaining data types, and they're painful. I think there's an F word, which is like a weird 48-bit, just kind of a hold back to a previous era of just a different era of things. So here are the rest of things. Okay, so let me take a pause here, and we'll talk about Endianness here in a second. Okay, so what you have to remember for everything we're doing in this course, I'm running on an x86 machine, and I'm never going to be able to change the processor because I'm writing x86 assembly language, is that we're going to deal with little endianness. So remember, it's the complete opposite the way you put the data into memory as if you would write it on a piece of paper. So like I said, if this was my 32-bit value, 1, 2, 3, 4, 5, 6, 7, 8 hex, and I tried to put that value into RAM, notice, maybe it goes top to bottom, but think of it left to right. It goes 7, 8, then 5, 6, then 3, 4, then 1, 2. The most significant byte is put at the highest memory address. And again, who wouldn't want big endianness to win? Because then it would be written into memory the exact same way it's drawn on a piece of paper. Win-win for everybody, but quit crying, Brad. Move on with your life. Find other things to complain about. So just to say, this comes into play a few times, especially when we're looking at memory 1 byte at a time. And we'll see also in the future that, again, if we don't care about memory at the byte level, we never have to really worry about the endianness of anything, at least in the scope of the course we're taking here. Okay, so arrays. Arrays are a tricky thing. Everyone hates arrays. Why is that? That's because arrays in assembly language are different. They're the same, but they're different than arrays in C++ and Java and high-level languages. So what happens? What is an array but a contiguous block of memory where every element of this array is the same data type, right? I mean, that's basically, if you want to think of it that way. So if I took this array byte 1, 2, 3, 4, notice how it's initialized here. This is a 4-byte array. So it's, this would be equivalent to character array 4, something like this, right? So it's a character array. There's 4 elements to it. Oh, and then 1, 2, 3, 4, something like that. Depending on the language, that's how I would represent this in C++. And so what that means is every byte is an element, right? Because it's a byte-sized element. And so at some location, wherever the array starts, that's where the 1 would go, then the 2, then the 3, then the 4. And so this is the binary representation of it. And this is the way you access the array as if it were C++. You know, array is the name of the array, and then the square brackets is the indexer to tell me which element to find. And so for all byte, these are all byte arrays. You can see they're because they're 1 byte at a time. We don't have to worry about that Endianness nonsense or anything like that. But you can see 10, 20, 30, 40, 50, 60, 70, 80, and so forth and so on. I hope there's no typos in there, but you can see, and we're going to see too, that we can access the array the same way in assembly language with the square brackets as we can in our high-level languages. Like, it's going to be tricky to do, especially when you see the next slide or the next slide 2 up for wherever it is. But for now, understand that we can still access things the same way. And so this is one of those crazy ones, just combining everything into one. Leave the first byte uninitialized, put 32 into the next one, 41 hex, and then this binary result into the next byte. And so there you go. And again, the 500 is just made up every time you run your program. This thing's going to be in a different place. And so just to say here, like values double, or we haven't done it yet. Byte 1, 2, 3, 4, something like that, right? So name of the variable, or name of the array, its type, and then its initialized values one after another. Oh, yep, okay, so here's one more byte using the same kind of stuff. And now again, this is where things get a little trickier. Okay, so we're dealing with words, which are 16-bit in our environment. So that means that every 2 bytes holds a value. And so notice how things are a little more spread out now. And because they're more spread out, the Endianness of this all starts to play a role. So little Endianness matters. And that's why the byte that has the 1 in it goes first and not last. Because again, the way we write it out in byte order is the reverse of how it goes into memory. So 1, 0, then 2, 0, then 3, 0, then 4, 0, then 5, 0. That is the representation of the 10 bytes of memory. And so what you see here is that array 0 is 2 bytes. And so we're going to see here that in C++, when I try to move pointers around, because it knows its type in C++, it knows how many bytes to move. And so, like, pointer plus 1 for an int pointer will move over 4 bytes. But in assembly language, we can only move bytes at a time, 1 byte at a time instead of elements at a time. So we'll see that in the future. So here's the Doop operator. So this is a fancy way so I don't have to write out, if I wanted 10,000 elements all initialized to 0, I don't have to spend half of my life getting carpal tunnel doing 0, 0, 0, 0, and so forth and so on. I could do something like this: values byte 10,000 Doop, and then put the value inside of here. And this will work perfectly fine because now I have a 10,000 byte array all initialized to 0. Okay, so same, and now double word is the same deal. Double word are integer values. So every element is 4 bytes of storage for double words of any type, signed or unsigned types. So notice things are spread out even further. And again, the Endian order matters. Notice over here for the positive 1 in these 4 bytes of storage, the 1 goes first and then you get the zeros because it's the way the Endianness works. And so just to say, you could do arrays of any type. Again, don't worry about this. The real 4, I just went ahead and just figured out what the IEE standard for 1.0 would be. And notice it's copied in there 4 times over. Okay, so let's see. Okay, so we talked about the Doop operator. We don't have to worry about all the craziness it can do, but just again, understand it's there to be, it's a convenience operator for you, so you don't have to just type out over and over and over again, the same kind of stuff here. And so what are the rules? What value are we duplicating and how many times are we duplicating it? 20 times 0. A defined array must allocate the amount of space that can be calculated. And this is why there's a difference in higher level languages between like arrays, static arrays, and like vectors and dynamic arrays and things like that. Because at compile time is when all the global variables are set up at compile time. So runtime plays no role. So if you're just like, I'll tell you when the program starts how much memory I need, that's not going to fly. You need to know how many elements to set aside, how big is this data segment at compile time. So it's a static event here. And so the duplicated values are copied into the array. So literally you're copying, there are values sitting in this program, they get copied into RAM, into the data segment, for those initialized and uninitialized values. So it's kind of cool how it works, because it's like, how else is going to put a 9 there? It has to literally move a 9 somewhere, and how would the program otherwise know? It has to be sitting in your program to be able to move it into RAM. Okay, so strings. Because we're using ASCII characters for strings, strings are byte sized. So just to change things up here, say my name, byte, put in quotes, Bradley Sward, and then a comma 0. So strings are either enclosed in single quotes or double quotes, as I was describing earlier. And say some people, you don't have to, oh my god, right? Can you imagine doing this every single time for every single character? So this is the only time like an array works out for us where we don't have to, like, you can't do that for integers. You can't just be like 1098, because that's just, how would it know? But I can do that for an array of character values. Bradley Sward, comma 0. And so you have to remember the null terminating character, especially if you're going to print these out as strings. If I'm going to use an array, I don't need a null terminating character. Array, because you're using an array differently. A string is it's the same concept, but it's used in a different way. And what will happen is, if you forget the comma 0, especially if you have another name, something like this, if you forget the null terminating 0, it'll actually keep going and blow through your entire data segment, printing out character after character after character until it hits a 0. Because that's the whole point of the null terminating character, is to make sure that, like, that's basically saying, this string is done, please stop. And so here are some more examples. Enter your name, oops, oh no, I forgot the comma 0, or halting. And like with this, if this is more of an array than a string, then you don't necessarily need the comma 0, because you're going to know how far you need to go in the array. And you can combine things onto multiple lines, so you don't have to worry about having things go off thousands of characters on the screen, because you want to keep things compact. And again, you can use single quotes and double quotes, and you can enclose. I've never had to worry about it, but you can do that. So this shows you how you can go ahead and basically set up one long string, right? The checking account, this is a whole menu in one line of code, or just one long string. And of course, the ODH and OAH, those are the carriage return line feed characters, basically your /n, automatically put in. So this whole thing, byte, just as long as you keep going, it will continue, because it's just an array, and you're initializing the entire array to this long string of data. So it'll print out over 7 lines, because this gets you to 2 lines over. Yeah, you can kind of see this is next line, but then a whole line. This gives me 2 lines, 3, 4, 5, 6, 7. Actually, it might be 8 lines. Might actually be 8 lines on the screen. I'm not going to try it out. Okay, so again, there's a big difference. Carriage return line feed, just to talk about what that means. We get spoiled with the /n, because /n is just one character. But say the computer, especially when it came to printers started out as just typewriters that were attached electronically to a computer, because it's just kind of how it was. And so to be able, what do you do on a typewriter when you want to go to the next line? And some of you have never even seen a typewriter, like these children, and my child probably hasn't. Where has he seen? He's seen it on like Sing or some movie he's been watching, but he doesn't know otherwise. And so to go to the next line when you're typing on a typewriter, you have to do 2 things. You have to basically hit the carriage return, which takes, basically your cursor, where would the next key go, and brings it back to the front. And then you have to advance the piece of paper so that you can, so you're not writing on top of what you've already written. That's the line feed. And that's exactly what these things represent: carriage return and line feed to go to the next place. Like go down, go back to the start of the, the start of the line, and then go down to the next line. Okay, so here is an example 32-bit program. So this is more, notice how, that 16-bit program I told you never to use, this is a lot more like it. There's less to worry about, right? There is no .386 and do this and, dot this and dot that. And so I don't know why this is, this is just a slight typo for me anyway. And you can see here, here's my data segment. Here's 4 separate variables. And I'm initializing them to these hex values. This one's uninitialized. They're all double words. And so that's my global section. And now there's code. And again, don't get too worried right now, since we had never talked about individually any of the operations, but it should make a lot of sense as to what we're doing, especially as I describe it here. Let me move my body over. Here we go. And so what you can see here is that this first line of code takes value 1, and which is 10,000 hex, and copies it into the EAX register. So essentially a move operation is an equals. Okay, and so next I'm going to add EAX comma val2, and as I'll say now and said before, add is like a plus equals operation. So that means EAX equals EAX plus val2. So I take the 10,000 hex that was previously in there, I add 40,000 hex, I get myself to 50,000 hex. Subtract is the same thing, but it's a minus equals. So I go, okay, what's in there now? 50,000 hex, subtract out 20,000, and I'm left with 30,000 hex. And so the last item here is moving a value into the variable. So basically this was 4 lines of code in assembly language that was basically final val equals val1 plus val2 minus val3. That's basically what was going on. You would write that in 10 seconds at the most in C++ or Java, but you would have to write 4 lines of code here in assembly language to make it work. And then we called dump regs just to show that we actually got the correct value into the EAX register, and yes, it would work perfectly fine. So here is what that call dump regs would actually show. It's an example output, again, because every time you run this program, your registers are going to start in a completely different state. So because the registers are being on the CPU are being used by many different tasks at the same time. So basically you just get whatever you get, and basically uninitialize registers. So so it's going to be different every single time, at least when the program starts. But at the end of the day, the only thing that matters is, because I ran all this code, EAX better hold my 30,000 hex. Who cares about anything else? But as long as EAX, because I said EAX is basically holding the result of that operation, all of these operations, that better be correct inside of that register. So you would know if I was debugging and I would print that thing out and it's not right, somewhere along the line I'm screwing up. So I mean, that's pretty obvious. I mean, it's hard to know when you're writing a ton of code where the breakage is, but if you break it down line by line by line, you can generally, especially in assembly language, you can generally see where the break occurs. Okay, so one of these little things here is the $ location counter. Just describe it pretty quickly. You hardly ever use it, at least in this course, because there's really no, it's kind of a crazy cool kind of thing. And so it's an operator. And so with this operator, with this $ operator, we can calculate both the size and the number of elements of an array. And so that's one of the, we can automatically do this without having to hard code the values. Because a lot of times, especially in C++, like if I'm sending an array from like a function to another function, I have to pass a pointer to the array, and then I also have to pass its size. Because when I pass a pointer along, I lose that information. Because it goes from being, maybe it's a global, or maybe it's something inside of like a main function, but I lose the size when I go off and I just pass along a generic pointer to a function. So that information is gone. But if I'm doing things globally using this $ operator, I can actually make this thing work. And so here are a few examples here. So the $ operator, so it's kind of like, how do you describe what it is? It's basically, if you start, because the data segment is where I put all of my code. or not at my, all of my global variables, one by one by one by one by one, as closely compacted as possible. And I have to start somewhere. Basically, the array starts at location 0. And when I'm starting off, and I start off, let's just say empty data segment, the $ operator is essentially pointing to the first byte of the data segment because nothing has been put in there yet. And so basically the $ operator is basically, or answering the question, or just answering, if I were to put another variable, a global variable, into the data segment, where would it go? That's essentially all it's doing. Because right now, if I were to put a variable in there, it would go in the first byte of the data segment because I haven't put anything in there yet. And that's exactly what this is doing. I'm saying, okay, list, set up a bite-sized array, put 10, 20, 30, 40 in there. And so, like we said, and they're bite-sized. And so now the $ operator moves over accordingly because it's done what it needs to do and set up everything. And so if I put up, like with these guys, I'm setting up these two variables after it inside of memory, well, where would they go? They would go 1 byte after the end of the array. So, and this is where things are fun. This is actually a minus operator. So I can say, okay, this is where list is, because this is where the first byte of my array is stored in memory. And I go over and it's 4 bytes, but here is list, and I go, the $ operator is now pointing here. And so you're like, okay, take $ minus list. And that's basically how many bytes are there between here and there. And you go 1, 2, 3, 4. And there you go. The number of bytes I used from here to there is 4. And then you go, well, okay, now that I know that, how many elements are there? And you're like, okay, well, it's this minus this. And you're like, well, that's 4 as described. And we divide by 1 because every byte is 1 sized. And so you get the number of elements is 4. Perfectly fine. So and what's cool about this is it's like by doing things this way, if I change the array later, I don't have to remember all the other places that I have to fix. Because this is now, these two are tied directly to this. So everything I change here, when I go to reassemble, everything else will work accordingly. So these are just examples of these are just larger examples. So for list 2, I'm putting a 50 in, I'm putting a 60 in, I'm putting a 70 in. And now the $ operator is pointing 1 past everything. And so now the question is, how many bytes are there in this second array of words? And so this minus this is 1, 2, 3, 4, 5, 6 bytes of storage. 3 elements times 2. And how many elements are there total? You do this, you do the same stuff. Take this minus this, which is 6 bytes, and you divide by 2. And you go, oh, that's 3 elements. What do you know? And the same now goes here. Now, this is where the $ operator add an 80 and a 90, but these are double words. So every one of these are 4 bytes of storage. So now here is the question mark again. And you're like, well, here, question, $ minus list 3. 1, 2, 3, 4, 5, 6, 7, 8 bytes. Because that's how many bytes there are between the two locations. And then divide by 4 because every element is a double word, and I get 2. There are 2 elements inside of this array. So again, pretty cool stuff. Wish you could get away with this in C++, but it's not always as easy. And this is, you can only do this in the global data, the global variables in the data segment. And it's basically the $ is at this current moment, where would the next variable go? So like you have to kind of do things in order. You can't just set everything up and then come back and fix all of this up, because the $ operator would be over here. Because if I did $ operator minus list 1, I would not get the same result after fixing all of this up as I would if I do it immediately after setting up just the first list. 2 more slides and we are done. So again, we could totally cover, because 64-bit programming obviously exists since we're working on a 64-bit processor. However, again, we're not going to be doing things in 64-bit mode here in class, so don't put that code into your submissions. You will get a big fat 0 and a reprimand for that. And so, but MASM fully supports 64-bit mode. And again, you're not missing out on anything. And again, 16 to 32-bit, that was more of a revolution of sorts. 32 to 64-bit is more of an evolution of sorts when it comes to things. And so you're not missing out on just changing EAX register to RAX and things like that. And so other directives fall away when you move up to 64-bit mode, because it's almost starting to kick away and almost to start to just eliminate 16-bit mode altogether. So a lot of this stuff, because what year was a 386 computer? Anybody know? That was right around 1994, 1995. So we're talking 25 years from now, or 25 years now. And you're like, well, goodness gracious, I don't think we have to worry about 386 processors in the modern day. A few people still have to, but not many. And so, and there are other illegal directives in 64-bit mode, but we don't have to care because we're not going to be doing it. So just to say here is a program that would work in 64-bit mode, and it's the exact same code as it would work in our 32-bit. If we just use the 32-bit registers and set up a double word and so forth and so on, this program will look identical. So again, you're not missing out on anything at all. The same program you write in 32-bit mode, you could just step it up into a 64-bit compiler, and with minimal or no changes will work just fine. And that is it. That covers everything I wanted to cover in this video. Hope it wasn't too long. I do these in sections, obviously, so I don't know. Hopefully not 6 hours of work. But anyway, so as always, if you have any questions, swardb@cod.edu is my handle. Or you can comment down below. Don't be a bot. I cancel all those bots out real quick. Send me a real comment, send me a real question, and I'll get back to you as soon as I can. And so this is step one. Next video should start covering the basics of actual assembly language, of getting real operations working. We already kind of alluded to them, but we will discuss them in greater details, and we will push on to bigger and greater things. So thanks for sticking it out with me, and I'll see you next time.